Okay, got to kind of catch my breath between classes, three classes in a row with 5 minutes between. If I forget what course I'm in here, uh, correct me. I'm going to take just a second to do this. And if you would, just put into the chat, just say hello and to confirm that you can hear me and everything. That hasn't been a problem in previous classes, but yeah, got at least one hello. Yeah, got a lot of hellos. Okay. And waiting for a couple more, but that's all right. Hopefully I've got enough board space because I want to take time to clean boards in an abbreviated class. Quick word about the homework. I think I've gotten most of the homework from most everybody. Maybe I've gotten all of it from everybody. I haven't been able to get through all of it. There were some serious glitches yesterday. Cost me a couple of hours that I've had. And I don't like to do the homework until I've got it all. One thing I'm going to ask you, and I'll email this request too, is do one of two things. Either send me, if there are multiple assignments due, either send me one assignment at a time, like 2.1 in a different document than 2.2 and a different document than 2.3, or send them all in the same document because I'm having a lot of trouble. You know, if I want to go through 2.4, I've got to find where this person do 2.4, where this one do 2.4, and so forth. And it slows me down a little bit to have to do that. And also in your email, put the heading, the section number. Okay. And if you do multiple sections, make sure it's all of the sections that are due at that time. So either all or one at a time. Okay. Couple of things that I saw in the homework. Saw this one fairly frequently. That's about what I saw, okay? Now that's right, but I have no idea what you did to get that because there's not even a scale on the diagram. So you might say, put a scale on this. You might just draw the circle. It's not a very good circle because it's not very good. And indicate that circles r equals 3. That's not part of the thing you were asked to do. Or just put a arrow here with a 3, but put a scale on it. Also, you really need to show me how you got this. Okay. I think this was three sine of 2 theta. And in order to understand this, other than just identify that, that's a 4-petaled rose, show me, and it doesn't hurt to make a table. Okay, it's good that you can identify that as a 4-petaled rose, but if you don't know what's going on between R and theta, it's going to cause you trouble. So theta is going to be your independent variable. What happens? If theta equals 0, then you're on the line theta equals 0, which is the pole. And of course, the pole, you don't really have X and Y axes, although we often draw them. But here's your pole. Angle 0 if the pole is along the pole. If theta is 0, r is 0. Then, if theta is pi over 2, r is 0 again, because you have the sine of 2 times pi over 2. That's the sine of pi, and that's 0. Okay, well, that's confirmed. If you go at the angle pi over 2 with respect to the pole, you're going in this direction, and the only point you got is the origin. Okay. Well, what about halfway between pi over 4? You double that, you get pi over 2. You get r equals 3. Because 2 theta is pi over 2, which is like 90 degrees. Sine of 90 degrees is 1. And 3 times that is 3. Well, that's what gives you this point. Now, I drew these things a little too flat, but if this is the theta equals pi over 4 line, then you got to go out 3 units, and you get this point. And then if theta was pi over 8, and be half of pi over 4, then double that would be pi over 4, and the sine of pi over 4 is the square root of 2 over 2. So if I just do a little erasing here. Pi over 8, you're going to get 3 times the square root of 2 over 2, approximately 2.1 something. Okay. 2.121 or 2. Actually be about 2.3, 2.31, something like that. Yeah. Oh, pi over 8 is here. My angles aren't very accurate, and this distance is like 2.1. Now I've slopped that all up, but you get the idea. You got to be able to make a table and understand what numbers to use for the table. And then if you go over into the next quadrant, the sign is still positive, so you'd be getting positive values. Then if you go into this quadrant, I'm sorry, go to this quadrant, you're going to get negative values. That's going to give you this loop for angles in this quadrant. For angles in this quadrant, you're going to get this loop. For angles in the fourth quadrant, you're going to get this part of the loop. And you need to understand why, and you need to understand how that comes about. So it takes a little bit of graphing and so forth. Review this. Also, some people ended up with graphs. Let's see. Get one person ended up with a graph that looks like this. Okay, and it was essentially in many cases, in many events, right. I forget what the function was, and I had to change gears. I thought we were going to be able to meet face to face this morning. Didn't find out until kind of too late. So I don't have exactly what I need here. In any case, there was a curve that was given this shape. It was obviously going to, okay. Well, what happens is theta goes to 2 pi over 2. what happens to R? Well, let's just take some different thetas. Here's theta equals pi over 4. Here's a sequence of thetas. You can see that if this curve continues, the trend that's kind of obvious here, as theta approaches pi over 2, R is going to approach infinity. Okay, and that's not what happens. The actual curve would be like a square root curve. It's a parabola in two directions, I think. And there's a cosine involved. No, I guess it's a, yeah. Maybe it's secant. But you get like an infinite slope when R equals pi over 2 or 3 pi over 2. Okay. And you got to understand how this happens in order to get this. Okay. In order to see what the shape ought to be. It's clear the function clearly was one where R did not approach infinity at pi over 2. And it did approach infinity at, I'm sorry. Yeah, R didn't approach infinity at pi over 2. R was 0 at pi over 2. And R then approached infinity as you went in this direction. So as the angles came down here. Okay, those kind of things. Take another look if you're making any of those errors. Some of you did quite well. Nobody showed me how they got this curve though. And several people had that curve. Other things, some people graph these things as it was a as if it was rectangular coordinates. So there was one problem where somebody got, and I think I saw this more than once, maybe a graph that kind of looked like this, and then this, and then this. You're not going to get a graph that looks like this in polar coordinates, R versus theta. So I think what somebody did was they graphed the function, but they treated R as Y and they treated theta as X. So they were graphing on a R versus theta set of X. And that's not what we're doing with polar coordinates, okay? So if you did that, you probably did it in a couple of graphs. And people did that, you know, most of the work on other sections look just fine. But here, here's a big misconception. So you want to think that one through. In case I need this board, I'm going to quickly wash it off. Set it aside. Be available to this later. Okay. Okay, for next time, and another problem I have is my Acrobat is acting up, so I'm having trouble. It's going to take a minute. Okay, didn't take that long. Okay, sorry for the delay, but what I've, what I want to do here is I think the assignment that I'm going to give you is section 1.5 on conic sections. And in general, in most cases, I didn't see enough detail in the section on polar coordinates uh, to give me a lot of confidence that people have a strong background with conic sections, and you need that. And you need the conic sections to do section 2.6, I think it is, on quadric surfaces that we'll talk about on Tuesday. It's really neat stuff. So I'm going to assign 1.5. I wanted to assign 2.6 as well, but I can't assume that people know conic sections well enough to do 2.6. So I'm going to go over the conic sections here in a minute. And then figure 3.1 and 3.2, because we've already pretty much talked about much of this. Except maybe I already signed 3.1. So it's a mess. 3.2 is on space curves, moving in space, unit tangents, components of acceleration and so forth. So we've already talked about that like on the first day. So I think people will be in fairly good shape on that section. Give me a second so we can actually get into stuff. Yeah, I just wanted to confirm that I was remembering that correctly. Okay, conic sections. Now I'm going to get rid of this. I kind of think I remember drawing this, but I don't. I'm sure. Okay. Bottom line on conic sections. Got a rectangle here. Can be any rectangle, but it's centered at the origin. I can draw an ellipse. If this is a square, I can draw a circle. Just got to be parallel here. Got to be parallel to this line, got to be parallel to this line, parallel to this line, for an instant at each of these points. These are called the vertices. So start here and come up here, come down here, come down here and up here, and draw a halfway decent ellipse. Kind of got a little ragged on the left. Looks pretty good on the right. Okay. Now, this distance is A, and this distance is B. Since the origin's at the center of this rectangle and it's oriented parallel to the axis, then this is B, and this is B, and this is B, and this is A, and this is A, and this is A. Should be obvious. Okay, this is an ellipse. This is the first thing I want you to know about an ellipse. Now, if you've got an ellipse that's centered at something besides the origin, centered at HA, then the equation is x minus h, quantity squared over a squared, plus y minus k, quantity squared over b squared, equals 1. And I keep advising you to make sure you understand transformations at the level of pre-calculus. It's just a horizontal shift and a vertical shift. And that's what happens to x and y when you shift the origin to the point HK. Okay. How to know this? Another picture. Rectangle. Of course, the rectangle could be elongated in either direction. But again, we got A here. We got B here. And this is the origin. Label that origin. I draw and extend the diagonal lines. And then I draw my curve. Curve goes through this point, and another part of the curve goes through this point. Maybe. Could go through this point too. And the curve is going to be tangent to the boundary of the rectangle and asymptotic to these diagonals. The only way you can do that, the only reasonable way to do that, or the smoothest and quickest way to do that is this. Okay, and you can do the same thing here. And of course, these are symmetric. You have symmetry with respect to the y-axis. Okay. Then this is the hyperbola. And it's x squared over a squared minus y squared over b squared equals 1. Now, there's another one. Now, these are called vertices, and these will be called vertices. There's another one up here. A lot flatter, but it does exactly the same thing. It's just that didn't do a good job on that, but okay. Kind of a flatter hyperbola. And x y squared minus over b squared minus x squared over a squared equals 1. Okay. So these equations are just like the ellipse, except one of the things is negative. Now, how do I know that this goes through this point, which is B A, A 0? Something's wrong. No, that's not wrong. Okay. Sorry, not quite with it today. It goes through A 0. Okay. When x is A and y is 0, you get a squared over a squared equals 1. Okay. There are no points between x equals negative b and x equals b. Because for any of those points, x would be less than a. And if x is less than a, x squared over a squared is less than 1, right? And if x squared over a squared is less than 1, there ain't nothing you can subtract from it that gives you 1. And of course, this is a positive number. There's no positive number you can subtract from the number that's less than 1 that gives you 1. So that's worth digesting. That's why you have a big blank between here and here. The other side of that coin is, if you have this one, and no, I got it right. Okay. This point is the point 0b. X is 0, y is b. Again, you get b squared over b squared minus 0 equals 1, 1 equals 1. If there's a y that's between negative b and positive b, then the magnitude of y is less than b. And y squared over b squared is negative. It's less than 1. And x squared over a squared would have to be imaginary in order to make that work. Again, there's nothing you could subtract from a number less than 1 that would give you 1. There's not a positive number less than 1. It's not a positive number you can subtract from a number that's less than 1 to give you 1. So you can always conclude from the shape of this thing or from the reasoning on the equation which way the hyperbola opens. Now, these things can also be rotated in space. If you have linear algebra, you know the rotation matrix, cosine of the angle, negative sine, sine of the angle, cosine. 2x2 rotation matrix. Now you can rotate these things, but we're not going to mess with rotation in this course. With a little linear algebra, it's fairly easy to do that, but the form of the equation gets messy. Okay, those are two basic conic sections. They're going to have to read where conic sections come from. It's a fairly simple thing. You got a cone here, and you slice it horizontally, you get a circle. You slice it a little bit more in this way, you're going to get an ellipse. Slice it this way, you get a hyperbola. And you look at the pictures. I'm not going to draw it or gesture it. It's fairly easy to draw. I could draw it. And if you slice it just right, you get a parabola. Okay. I'm going to confine myself to hyperbolas and ellipses. I'll say a little bit about parabolas, but I'm not going to draw the picture. You know what a parabola looks like. It's like an x-squared graph. Now, a little more general. The equation for a conic section. Now, A and B, I'll use capital A's and capital B's to don't confuse them with the A and B I used on the pictures I drew. There's the general equation or the general form of a conic section. if there's no rotation. If there's rotation, then you got a term xy. If A equals B, then when you get done completing the square, you get A times x minus h squared plus B times y minus k squared. And that takes care of these four terms. That equals negative E. And should say if A equals B not equal to 0. We get this. Yeah, well, if E is positive, negative E is negative, and you got the sum of two squares. I got to put one more condition on A and B. I apologize. If A equals B, which is greater than 0, that means both A and B are equal and positive. Okay. And for equal and positive, you get this. And we can divide by negative E. And negative E, of course, is positive if E is less than 0. And do negative E over A here, negative E over A here. So that works. E over B. And all this does is shows you that you can get an ellipse. If A and B are both positive and E is negative, you get an ellipse. So you get an ellipse out of this form if you have the right numbers. If A and B have opposite signs, then you want to write it that way. Okay. You have plus or minus x minus h squared over a squared, minus or plus y minus k squared over b squared equals 1. Now, this depends whether a is positive, b is negative, a is negative, b is positive, whether e is positive or negative. It all comes down to that. And the plus and minus, minus plus. That just means that this has the opposite sign of this, and you get a hyperbola. Magnitude of A is square root of the magnitude of E over big A, etc. And you should understand those algebraic things. If you want to think about it, your book will tell you about it. If A times B is 0, and A plus B is not equal to 0, what's that mean? That means AB equals 0 means either A equals 0 or B equals 0, right? The only way you can multiply two numbers and get 0 is for one of them to be 0. And they could both be 0, which is why we have this characteristic, or this thing here. A plus B is not equal to 0. This means either A or B is 0, so one of these is 0, but when you add them up, you don't get 0. That means the other one isn't 0. You get a parabola. For example, A equals 0, you get, I did something really boneheaded over here. I said this is equal to negative E. And I've used E's all through these. I can't use E because when you complete the square, you gotta, add A times whatever the constant is here and B times whatever the square of the constant is here. So I gotta call that F, and I don't need a negative sign on it. And actually, F has to be positive in order for this to work. But if your E is negative enough, F won't be positive, so go from there. So my E's have to be F's. And that accounts for what happens when you complete the square. Okay. When you complete the square, you gotta add something to both sides. That's gonna affect you. Okay. In any case, if A equals 0, what you get is B times y minus k squared. I'm gonna get something of this form. So this is like x equals y squared, which gives you a parabola on its side. It might be this way, it might be reversed. And if B was 0 under these conditions, you'd have y equals x squared type graph. I don't want to go into the detail of that because it's pretty easy to rearrange these if you know how to complete the square. It's just kind of a picture of the scope of the conic sections. You need to know how to graph them. It's good to know their definitions. With what we do with quadric surfaces, and we'll be doing it next week, is a quadric surface is a three-dimensional surface, which if you cut horizontally or vertically or actually in just about any direction, the plane of your cut intersects the surface in a conic section. I'd recommend you kind of read ahead to section 2.6 so you know why you're doing the conic sections. Okay, now that's all I'm going to say about conic sections. It's actually part of the prerequisites for this course, but I know that in some sections of pre-calculus 2, it doesn't get done. So people come in, some people come in very well prepared with conic sections. Some people come in completely unprepared. So that's what section 1.5, yeah, is about. So make sure you work that through. And use this trick when you're drawing the ellipses and hyperbolas. It allows you to draw a pretty good ellipse or hyperbola without plotting a whole bunch of points. If you just draw your rectangle, wherever the center is, if it's the origin, fine. If it's at HK, well, you're going to get this. Okay. So I don't want to talk any more about it, but if you're having trouble with it, please let me know and I'll do what I can to help you through it. There's one more section in chapter 1 that we need to do. It's area and arc length in polar coordinates, but I want to be sure everybody's had the opportunity to nail down polar coordinates. We can do that. We can do that next week. And it doesn't really hurt. You don't need the polar coordinates for much of anything that's being assigned between now and next week. And then we wrap up completely chapters 1 and 2 and move well through chapter 3. So that we get into chapter 4, which is where things really get interesting. Okay. Now, just to kind of review, section 3.1 is fairly straightforward. I don't think you're going to have a lot of trouble with it. You got to be able to do some limits and know what continuity is and domains and ranges and stuff like that. But it's all pretty simple and straightforward functions. Again, if you have a lot of trouble with it, if you got a question or a problem, email me. Of course, you can always go to AI. And remember my warning, don't let AI do your work for you. Let it inform you about the topic, but don't let it do your problems for you. Got to switch back to the screen. Okay. So just a quick recap, stuff we've already talked about. Okay. This function is defined wherever all three of your x, y, and z parameters are defined, okay? Well, T is your parameter. These are parametric. Yeah, this is equivalent to parametric equations, x equals x t and so forth. Okay. And I think people are pretty good with most of the stuff in parametric equations. Just to review, R prime equals x prime I plus y prime j plus z prime k. And I've left the parentheses t. It's understood that x, y, and z are functions of your parameter. And r is a function of t, and v is a function of t. And v is the derivative of r. At your velocity. You have a speed and a direction. And you've done enough homework with unit vectors and so forth to have the skills to completely analyze these things at the level of the text. Okay, so v, you think of that as velocity. You got your unit tangent vector. What you could write as v hat. If you do, be sure you keep the arrow on it because just plain old v hat means just a magnitude of v hat. And v hat is defined to be a unit vector since magnitude is 1. So you would never write v hat, that's just 1. But v with a vector with that arrow over it and a hat. You can't handwrite boldface very effectively. Okay, there's your unit tangent vector. Acceleration. See both those primes. The parallel component of your acceleration, we talked about it before, you're driving your airplane or whatever. And you want your acceleration in your direction of motion. That tells you at what rate you're speeding up or slowing down. Well, you do the dot product of your acceleration with your unit tangent vector, you get your parallel. It's like a curve here. And at this point, here's your velocity vector. Here's your unit tangent vector. And here is your acceleration vector. The component of the acceleration in your direction of motion is the projection of your acceleration vector onto the velocity vector, if you like, but more conveniently onto the unit tangent vector because you don't have to worry about dividing by the magnitude of v. And I think you should know what I mean by that because you did pretty well with projections as a class. Pretty much everybody did pretty well with projections in whatever section that was. Okay, section 2 point whatever. So I think that's pretty straightforward. You just remind you, theta is the angle here. So there's your acceleration. Your component of acceleration perpendicular to the unit tangent vector. Let me get a little more colorful here. Let's make the acceleration vector. I left something off when I did this. This is a vector, A dot T is a number. This can't be. But if you multiply, this is a scalar projection, and you multiply that by the unit tangent vector, and you get what we call A parallel. Then A parallel plus A perpendicular equals A. What's A perpendicular? Well, you draw it from here down to here, but we'll usually draw it over here. There's A perpendicular. And one way to calculate it is if A parallel plus A perpendicular equals A, and this is a right angle, you know, the tangent and the perpendicular, by definition, make a right angle. So you just have a Pythagorean theorem here. But the A perpendicular vector could be calculated by subtracting A parallel from A. Just solve that equation for A perpendicular. There are other ways to get it, and we'll talk a little bit about them, but it's one expedient way. It helps get the picture. The other thing is the perpendicular component is related to your curvature. It's what moves you, what accelerates you perpendicular to directions, so that you can go around curves and stuff. And we'll define curvature, your book defines it. It's the rate of change of your unit tangent vector divided by your speed. How quickly the unit tangent vector is changing. Corrected for the fact that it changes faster if you go faster, but that doesn't make the curve any sharper. Okay. And we'll talk about that in a little more direction. Now, all this ought to be familiar to you since we talked about it a couple of weeks ago. But at least it should jog your memory. This much will get you a long ways through section 3.2. We can go just a little further. The curve path, at least you're moving at a non-zero velocity, A and T won't be parallel. Both are in the plane of motion. In other words, at any instant, no matter how you're twisting and curving around space, at any given instant, there's a plane in which you're moving. And that plane contains your unit tangent vector and your acceleration vector. If you take their cross product, you get a vector perpendicular to that plane. So A cross T is normal to the plane of motion. Now, more usefully, if n, if we're going to call it normal vector, is equal to the unit vector in the direction of A perpendicular, then there's A perpendicular, and this orange vector is your vector n, which is a unit vector perpendicular to your unit tangent vector. So we use B as a symbol for n cross T. And T and B form a set of unit vectors. You don't need the word so there. And anything you do uses those vectors as a reference point. Those vectors change every instant if you're moving along some kind of a space curve. Okay, if I'm tilted this way, going that way, and curving this way, then my tangent vector's there, my normal vector's here, and my binormal vector is here, not straight up, it's here. Because as I'm oriented here, that looks like straight up, that looks like straight ahead, and that looks like center of my curve. So that's a pretty neat construction, and it keeps changing. The rate of change of your binormal tells you how you're turning in space. I can't really do that in front of the camera in a way that makes sense, but I'll practice my contortions and show you on Tuesday. So you want to think about that, okay? In their terms, there's pitch and there's yaw, okay? And we can associate those terms with the coordinate system you get that you carry with yourself as you're moving through space, consisting of the unit tangent, unit normal, and binormal, which is also unit. Because if you cross two perpendicular unit vectors, you're going to get a unit vector, right? Okay, well, I think y'all in pretty good shape with the basic vectors. Most of you need a little shoring up on the polar coordinates. And make sure you get the conic sections. Okay. Any problems? Things, any difficulties? It's nice if you let me know about them so I can address them in class. And of course, it would have been good if I would have been able to get through all of your homework. I got through a pretty good sample of it, but didn't get through the whole thing. Hopefully Zoom will behave itself today and I'll have this posted within a couple of hours, along with the AI summary. Remember, I want your feedback on the AI summaries. Do you find them helpful? Do you find them useful? What could I change? What should I change? What would you like to see me change? Because I can ask ChatGPT to do things in this way or that way or the other way. Okay, I can be very specific and we can evolve a way to get summaries that are more and more useful to you. It's not difficult for me. It's apparently not very difficult for ChatGPT. Hopefully we can get you some documents that are really helpful for you. Okay. See you on Tuesday. Questions are always welcome. Any comments, you can go ahead and put them in, but some of you are going away already. That's okay. Just email me. It says, who can see your messages recording on? Yeah, I'm not sure about that. So we'll see what the recording shows. 1531 and 32 over the weekend. I think so. I think I've already got the problem assignments up there, but I haven't completed the page for today because I don't have the videos yet, but you can look. And there's some other sections that are listed there that won't be assigned until next time, but I wanted to get them up there so I could organize things. So we'll get that organized within the next couple of hours. Anything else? I'm not in a big hurry here. Okay, thank you and have a good day. Have a great weekend. Stay warm. Look forward to Monday and Tuesday, which is supposed to be pretty warm.